So welcome to this class. Last class we have seen that how the artifacts comes up during the field evaporation due to the deflection of field lines. Okay, and it is directly related to the tip surface and the distribution of electric field. Especially these are crystallographically dependent. Okay, in this class we briefly discuss about the resolution. Spatial resolution. Okay, so for in the reconstruction or in the atom probe or the FDM, so the spatial resolution is usually highly anisotropic. It's highly anisotropic. Okay, so in the Z direction, why it is highly anisotropic? So we will discuss about this. If you have a needle specimen, okay, and as I told you, the field evaporation takes place when these atoms gets polarized and ionized, and they move along the field lines. So the atoms are field evaporated layer by layer. So it is a sequential process, sequential layer by layer process. Okay, so and this sequential process directly gives the depth resolution in Z direction. Okay, in Z direction, depth resolution. Okay, so because of this sequential layer by layer process, and this is due to the electric field penetration, which is much less than the despacing between the two layers. Okay, so this creates the depth resolution, and it is much higher than the spatial resolution. Why it is higher than the spatial resolution? Because the spatial resolution is affected by trajectory aberrations that we discussed in the last class. Trajectory aberrations, then local magnification effects due to the curvature. Okay, so spatial resolution is mostly affected by this, and the depth resolution is much higher than the spatial resolution. So now we will discuss about the depth resolution. Okay, the first thing which depends, the depth resolution depends, is the interplanar spacing. Interplanar spacing of the atomic planes. Okay, means the interplanar spacing of atomic planes, it is directly related to the size of atomic terraces. Okay, so you have a needle specimen, you have atoms, you have these atomic terraces, and if you see in this particular direction, if on the FDM or the field desorption map, these atomic terraces will be represented by concentric circles, and the distance between these rings is actually directly related to your interplanar spacing or the despacing. Okay, so we have a low index crystallographic plane, we have a high index crystallographic plane. Low index crystallographic plane, they have a distance farther apart, means they have a large distance between the terraces, large distance. But in high index plane, the distance between the terraces, the distance between the planes is very small. Okay, so that is the reason why the distance, the interplanar spacing will be a factor to determine the depth resolution. So for low index planes, as these are large terraces, then you can actually map these planes very easily, as compared to a high index zone where the atomic despacing is very small. Okay, so your depth resolution is directly depends upon the interplanar spacing of the atomic planes. The second factor is temperature. Okay, so as you know that field evaporation is a thermally activated process. Thermally activated process. So the probability of the field evaporation at that particular instant depends upon the temperature. Okay, this means that the accuracy of detection of sequence depends upon the temperature. Okay, now due to this temperature effect also affects the size of the atomic terrace around pole. Okay, that's why this has a direct influence on the depth resolution. Now we talk about now lateral resolution. Lateral resolution means in x and y direction. So you have needle specimen, so this is the z. So if you have a like then, so we will have a x and y direction. Okay, so usually if you see in film this lateral resolution, there are two main, in film we have discussed there are two main components of film where we talk about the lateral resolution. It is related to your thermal agitation of gas atoms. It means it induces the lateral velocity. So you will have a blurred image. And another is the position uncertainty of the gas atom or the gas atom of an atom. Okay, so these are the two important things which affects the lateral resolution. In FDM, field desorption in a microscopy image, this is actually limited by the trajectory aberrations. That is related to your distribution of electric field. So at a very low temperatures, your surface diffusion can be minimized, but actually the lateral resolution is limited by the thermal agitation of the surface atoms. Okay, so it means that the amplitude of thermal agitation should be much less than the distance between the two atoms and at a plane. Okay, so this is related to your trajectory aberrations in the field desorption microscopy image. So therefore the lateral resolution strongly depends on the tacking of atoms, which corresponds to the crystallographic direction. Okay, but still if you lower the surface, if you lower the temperature, still there will be some surface migration and rolling process which affects the lateral. So it cannot be avoided fully. So there will be some roll up process, or there will be surface migration even at much lower temperature. Okay, so in the case of laser pulsing, the lateral resolution decreases as your laser energy increases. Why? Because as you increase the laser energy, actually you are increasing the thermal agitation of the surface atoms. Okay, so there should be an optimum spatial resolution. Okay, so So there should be an optimum spatial resolution that consists of a depth resolution related to the order or the sequence. So here the high resolution obtained with the field evaporation occurs in a controlled manner. Okay, usually this depth resolution can be if we will get the very good depth resolution near to usually the poles or the zone lines. Okay, and lowering the temperature increases the influence of electric field on the evaporation field process, and that's why this improves your overall spatial resolution. Okay, so with this so in this we have discussed the effect of how a spatial resolution can be improved. So usually it is spatial resolution is divided into the depth resolution and the lateral resolution. As it is a sequential process, we say that these in the Z the resolution is much higher than the lateral resolution. Usually in the lateral resolution, these are affected by mostly the trajectory aberrations during FDM, field desorption microscopy, all the local magnification effects. Fine. So now as we finish this basics related to the reconstruction, what are the importance of parameters? What I will do is I will briefly go through the working principle of atom probe tomography, and so that you will get a revision for the in this course. Okay, so you can see that as atom probe tomography, there is a needle specimen, you are applying a DC voltage, there is a local electrode. Okay, and this is a MCP plate, and this is a PSD, this is a position sensitive detector, which is called delay line detectors. Okay, and this particular chamber is kept in a very high vacuum chamber, at a very high vacuum. The temperature is sub-zero temperature and 25 to 100 Kelvin. Okay, you are applying a DC voltage. When you apply a DC voltage, you will see that there will be a polarization of atoms near to on atoms present on the surface, and due to this polarization and the electric field on the tip surface, these atoms get ionized and they are accelerated along the field lines, and they travel through the local electrode, and it goes to the MCP plates. And these MCP plate, multi-channel plate, are nothing but the it converts the ions that are hitting on the charged glass tubes to a number of electrons. Okay, so it generates a number of electrons, and these electrons from the MCP plate, they are biased as with respect to the position sensitive detector, and these the number of electrons are hit to the delay line detectors. These are nothing but the conducting wires, and as it hits to the conducting wires, it creates a pulse, and the pulse travels along x1y1 and x2y2, and the time recorded in this process can be actually converted to the position of the hit. Okay, so in this process you are getting a sequence, you are getting x1 position, y1 position, and the time of flight. Fine, and the z coordinate is measured based on the atomic volume, and it is related to your sequence. Okay, and as I told you, the position of hit, the xy coordinate is around, the resolution is 0.2 nanometers, which is a lateral resolution. In evaporation sequence, the z coordinate, it is usually 0.04 nanometers, which is having a very high good depth resolution than the lateral resolution. The time of flight, you can identify the chemical identity by this basic equation, which is mass to charge ratio is equals to the 2 electron voltage applied time of flight divided by L. L is the distance between the tip surface to the position sensitive detector or whole square. Fine. So this is the basic equations which we get from the chemical identity. Okay, so we discussed about the two pulsing methods. One is voltage pulsing, one is laser pulsing. Fine. And in voltage pulsing, what you do is there is a DC voltage. There is a base DC voltage, and in the voltage pulsing you are actually increasing the voltage for few nanoseconds and you are reducing it. Due to this increase in the voltage, usually you are polarizing the atoms on the surface and they get ionized. So this sequential process with time, these are called voltage pulses. In the laser pulsing, actually you are increasing the temperature as a pulse. So you are creating a pulse, then you are increasing the temperature of the tip surface, again reducing, again increasing. So these are related to few nanoseconds of this pulse. Okay, so laser pulsing is nothing but a thermal pulsing, and voltage pulsing is nothing but the HV pulsing. Okay, so in HV pulsing, as I told you, to increase the electric field at constant temperature. But in thermal pulsing, the temperature, while the electric field is kept constant and the temperature is increased. So this is the difference between the two pulsing methods which we use in the atom probe. Fine. So we also discussed about the how measurement of time is done. So you can see that if you consider a pulse, okay, so once the pulse is applied, either HV or laser pulse, and as the pulse starts, usually what will happen is, as the pulse starts, there is a detection window which opens up, and this detection window opens for some time. Okay, so once this detection window is up, as the pulse reaches at the top, there will be a detection of the particular ion on the delay line detectors. Correct? It might possible that during these windows there may be a blank event, there may be a single event, there will be multiple events. Okay, and the time, the highest point of the pulse, there is a difference in the highest point of the pulse and the start of the detector window. This time difference is called T naught, which has to be taken care during the measuring of the mass to charge ratio. Okay, so this is how the measurement of time of flight is done. Okay, in this, the mass resolution is defined by m divided by delta m, which is the which can be a 50% or the 10% FWHM or the FWTM. Okay, and you are usually getting a peak. So you are getting a y-axis as the number of ions and x-axis is a mass to charge ratio, and you can see there is a width for each peak, and this width of the peak directly corresponds to your pulsing. Okay, it might possible that during HV pulsing, okay, during HV pulsing it might possible that at the top, if there is one ion gets detected, it might possible that the ions may be detected at these lower voltage values, and due to which this creates a spread in the detection of that particular mass to charge ratio ion, and it creates a broadening of these peaks, and this broadening of the peaks are directly related to your mass resolution, which is given by m by delta m. Okay, in the laser you are actually heating the sample. So the temperature when you each pulse, when you do each pulse, there will be an increase in the temperature, and as soon as the second pulse will come, the temperature has to come down. If the temperature doesn't come down with the second pulse, usually you will develop a thermal tail in the peak. So you will get a large peak and you will get a thermal tail. And this thermal tail, it directly affects the mass resolution, because the other mass to charge ratios which can be detected here can be suppressed with these thermal tails. Okay, this is the related to your laser pulsing. That's why laser pulsing, higher is the energy, lower will be the resolution. Correct? So you have to use the optimum laser conditions for this factor. Okay, and this resolution, as I told you, for voltage pulsing it is 500, and for laser pulsing it is much higher as 1000. HV pulsing, remember for conducting samples, HV pulsing works out, and for but insulators and the semiconductors, HV pulsing is very difficult, or it is very difficult as the conduction is very low, correct. But in the laser pulsing, you are playing with the temperature, correct. So usually it depends upon the how the sample the thermally it can conduct, correct. So usually for laser pulsing we use thick samples, so that the temperature which is kept on the tip surface can be removed very easily. Okay, so these are the factors which influences these are pulse fraction, temperature, voltage, and geometry of the tip. So you can see that we also discussed about the energy deficits in the voltage. As I told you, the ions which are when the voltage during HV pulsing, when the voltage decreases, it might possible that the ions at these time frames, it may get field ionized, it may get field evaporated, so it will be detected and you will get a broadening. Okay, these are called energy deficits. In the laser, the finite duration of thermal pulse, so that is a thermal tail. So as I discussed, the temperature has to come down, fine. So to reduce this energy deficits, we can use the energy compensation devices. These are called reflectrons. And for the laser, actually we can improve by the specimen geometry to make it a thicker specimen, and also the proper laser conditions for the field evaporation, correct. So for energy compensation devices, as you can see that this is a typically grid with a change in the electric field as you go into the grid. Okay, this is called a reflectron. So if there is a species which is having a mass to charge ratio, and if in the voltage, if some ions are field evaporated at this location and some field are at these locations, usually they have a energy difference. So what it does is the ions which is having a higher energy can actually travel into these field lines at a farther distance, while the ions which is having a lower energy will deflect much earlier. So overall it will reach both the ions will reach at the same position, nearly at the same position. So what will happen, your mass spectrum which is a thick, it will become a very thinner. So your mass resolution improves by using the reflectron. But remember, reflectron, you are increasing the time of flight, so you will lose most of the ions in the background, so your efficiency will reduce. Okay, so without reflectron, usually the efficiency can go up to 72% detection efficiency, but with using reflectron it may go up to the 52 to 57%, so it get reduces. Okay, so this is how increase in the time of flight can actually improve the mass resolution for both the pulsing modes. Okay, this is due to the correction for the energy deficits and also the finite duration of the thermal pulse. Okay, so this is, you can see that the mass spectrum, you can see that how much the thickness of these peaks has got reduced, but you can see the number of counts also reduced for these ions, correct. So detection efficiency. Now compositional measurements. Okay, so here there is a composition. We can measure the composition as the number of atoms of that particular species divided by the total number of atoms which are present in the needle specimen into 100. Okay, so this is usually calculated as the compositional measurement, and this particular is called a statistical error. Okay, which is given by Cj minus 1 minus Cj by number of atoms. You remember that it depends upon the total number of atoms in that volume. Okay, so this is how compositional measurements will measure it. Now, just briefly, from the instrument you have a X detector, Y detector, time of flight and voltage of the specimen. Fine. And in the reconstruction you use the reverse projection to get X tip, Y tip, Z, the depth and also the mass. In this with this way you can actually calculate the, you can map the three-dimensional volume of the specimen tip. Okay, so in the left side you can see these are the golden color atoms corresponds to aluminium, and these red color and the green color regions are the zirconium rich and copper rich precipitates. Okay, and in the right side, as I told you, Z depth, you can get the atomic plane resolution. You can actually map the composition of the atomic plane. So you can see that the each plane corresponds to 100 plane of copper. Okay, so this is called depth resolution. Briefly, I will go through it. The important factors that has to be considered: if you are an idle charge of a spherical, you have a field along the charge as voltage applied by the radius of curvature, but your tip shape is a truncated shape. Okay, so it is a truncated shape, and due to which your field lines are not homogeneous at each place. Okay, so this relates to your field enhancement factor has to be added to get the correct path of the field around the truncated needle specimen. Okay, and this, due to this shape of the specimen, the field lines actually these has to go along the perpendicular to the surface exactly at the locally, but it get compressed towards the axis, Fine. This is related to your near field and the far field electric field distribution, and this directly relates to your specimen specimen local curvature effects. Kind. So there will be always a ion trajectories which are compressed as per the field lines. So from the basic point projection model, actually you can assume that the atoms which are which assume that it has to be radially accelerated, that can be, and but usually it is compressed and it hit to the detector at this position at a distance d from the center axis. You can draw a straight line along with this particular atom which is on the surface and projected onto the axis to a point P which is far from the O. Okay, and the distance between the tip surface to the P is related to xi r, and the xi is corresponds to the image compression factor. Okay, and if you see the distance d from the tip axis to the detector hit, and the small d which is the distance from the tip surface to the projected two-dimensional plane of that particular atom on that plane, that d distance, you can, by the triangular symmetry, you can assume that m projection is related to d by d, and it can be equal to the L by xi r, and xi is called image compression factor, which is between 1 and 2. 1 and 2, 1 is due to the radial and 2 is when we consider as a stereographic projection. Correct? So these are the two important field factor and the image compression factor which has to be taken care during the reconstruction. That takes care of the field lines, the actual field lines which are distributed in the near to the tip surface. Okay, so this is an instrument which is at IISc Bangalore. So you can see this is a atom probe instrument, and if you see the cross section from the top view, okay, if you see cross section from the top view, you have a specimen transfer rod. So this is called specimen transfer rod. This is called specimen transfer rod. Okay, these are called carousels. This is the part which I am indicating. This is in this direction. If you see from the top, you will see these are the carousels. Okay, and this is called analysis chamber. Analysis chamber, and the chamber between the analysis chamber and the loading chamber is called a buffer chamber. Okay, so the sample is loaded in this particular loading chamber. Okay, and it will be passed on to the buffer chamber by using the specimen rod or the specimen transfer rod, and it gets fixed to the stage in the analysis chamber. Okay, so this is your atom probe specimen, this is your laser, this is your electrode, and backside there is a MCP plate, and this is your delay line detectors. Okay, so you are applying a voltage. You are applying a voltage between the tip and between the electrode, DC voltage. So if you zoom out here, so you have a needle, you have an electrode, so the ions get field evaporated along these field lines, and backside these are MCP plates and the delay for the detection. Okay, so this is your it's kept as a very high vacuum, and to maintain the temperature of the tip you use the cryo head, okay, which is supplied by helium gas to maintain the temperature of the tip surface. Okay, so this is the top cross section of the typical atom probe instrument. Fine. So here briefly I will give you the overview of the how the samples are kept. So these are called. So these I will discuss more on when your sample preparation is going on. So these are called silicon. These are called silicon coupons. These are called silicon coupons, and at these silicon coupons you can see that these are some protrusions. These are called silicon protrusions, which are called silicon posts, and if this particular the length of the silicon post is around 100 micrometer length, and if you see from the top surface, this particular diameter of that post is around 2 microns. Okay, so usually we'll paste the samples on this particular silicon coupon, and we'll make a sharp needle by using by focused ion beam. I will cover these topics in the later stage, and this particular silicon coupon is held on the copper clip, and this copper clip will be inserted to the chamber in front of the electrode. Fine. So this is how we usually put the sample inside the chamber. Okay, so I hope you got a good understanding of the basics related to the field evaporation, field ionization, and the difference between the atom probe, and the field ionization microscopy. Also, what is the field desorption microscopy, how it went through the atom probe tomography by using the time of flight spectroscopy, and we also discussed about several parameters which are responsible for the proper reconstruction. Okay, so we have discussed about the image compression factor, field factor, temperature, the types of pulsing, and what are the artifacts which usually will occur during the reconstruction of the sample. These artifacts, it might be induced by the experimentally. This is related to your local curvature effects that can be due to the trajectory aberrations or surface migrations or rollover atoms. Okay, so these all things can be controlled by the temperature and the type of pulsing conditions, okay, and the shape of the specimen. Okay, so with this I will end this class now, and in the next class we will more discuss about the sample preparation methods. Okay, so if we so I will discuss about the types of sample preparation methods related to electropolishing, and also the focused ion beam instruments. Thank you.